We're ready to start the final session of the Extended Sources in IXPE era session here at the EAS meeting. And our first talk of this session is by Josephine Wong, who's going to talk to us about studying X-ray polarization of pulsar wind nebulae with IXPE. So go ahead and take it away, Josephine.
Okay. So hello, everyone. Thanks for coming to this talk. And sorry I couldn't be there in person. So I'm a graduate student in the IXPE Pulsar Wind Nebula Working Group, and today I'm going to be talking about some of our findings using IXPE to study pulsar wind nebula using X-ray polarization. So to begin, so pulsars, they are the compact remnants that are left behind after a supernova explosion of a 10 to 25 solar mass star. And they're compact because it's about 1.4 solar masses packed into a radius of only 10 kilometers. They have very fast spin periods ranging from a few milliseconds to a couple of seconds, and powerful magnetic fields that span 7 orders of magnitude, so 10 to the 7 to 10 to the 14 Gauss. And pulsar wind nebula are powered by the younger pulsars with strong magnetic fields. So here's an image of a prototypical example of a pulsar wind nebula, the Crab, as seen by the Chandra X-ray Observatory. So these pulsar winds are relativistic electrons and positrons that have loaded onto the open magnetic field lines of the pulsar, which are wrapped around the pulsar as the star rotates, and escape the pulsar magnetosphere. They are dominated by synchrotron emission. And so when you look at the spectral energy distribution for these pulsar wind nebulae, they you would see broadband emission from radio to X-ray energies, and sometimes with a inverse Compton hump at gamma rays. They are also characterized in the radio by typically a flat spectrum. And these objects are interesting because they're sites of relativistic particle acceleration and shocks when the pulsar wind interacts with the surrounding medium. So they serve as laboratories for studying these phenomena. So IXPE has observed several of the brightest pulsar wind nebulae, and in chronological order, they are the Crab, Vela, MSH 1552, the supernova remnant VO 540, and G 21.5. But for this latter observation, we are still in the midst of writing up the paper. So I'll just be presenting our results on these 4. So the Crab pulsar is a 33 millisecond pulsar, and it has a surface magnetic field of 4 times 10 to the 12 Gauss. And it's located 2 kiloparsecs away with the characteristic age of 1,260 years. So its wind nebula has a very rich morphology. So around the pulsar, you can see in this Chandra image, a equatorial toroidal wind, as well as jets in the north and the south. Other features include these synchrotron knots that have been seen to disappear and then reappear on a timescale of like a few months, as well as shock fronts like the termination shock here, which is where the cold radiationless pulsar wind expands outward, and then it collides against the more slowly moving nebular medium around it. And that creates a shock front where these electrons and positrons are accelerated to ultra-relativistic energies. And then we also see whips that move outward from the termination shock, as well as this western bay where we see a lack of X-ray emission. So very rich morphology and a lot of dynamic structures. The Crab was the first confirmed astrophysical source of synchrotron radiation. So in 1954, they measured around 9 to 15% optical polarization integrated across the nebula, and that's a signature of synchrotron processes at play. And since then, we've measured polarization in wavebands ranging from radio to gamma rays. But most of our measurements have been in the radio and optical until now with IXPE. But first, I'll summarize some of our optical polarization measurements, since there'll be an interesting comparison to our IXPE X-ray polarization measurements. So here in the optical, we see using HST, they're able to map out the polarization patterns in the nebula. And they focused on certain regions in the nebula, such as the WIFs and the inner knot, where they measured polarization fractions of 40 and 60% respectively. They also found that the polarization angle in these regions is close to the symmetry axis of the torus. We've also in the past gathered high timing optical pulsar polarization measurements, so phase resolved pulsar polarization measurements. And there they were able to see a sweep in the polarization angle in the main pulse and in the interpulse, and also see that the polarization degree drops from around 20 to less than 5%. So there are some pulsar magnetospheric models that have attempted to replicate these optical polarization results, but they have been done with varying but limited success. So having X-ray optical pulsar polarization measurements to accompany these will be a very useful constraint on those emission models. Integrated across all phases, the pulsar has a polarization degree of 5.4% and a polarization angle of 96 degrees. So, and then by contrast, we only have a few polarization measurements in the soft X-rays. So the last one for the Crab Nebula was in 1978 using the OSO-8 satellite, where they measured 20% polarization degree, which yet again confirms the presence of synchrotron radiation in the nebula. So with that comes IXPE. So IXPE has measured or observed the crab for a total of 300 kiloseconds. But we only have results for the first observation so far. From that observation, we've been able to map out the polarization structure in the nebula. So that's shown here in these panels on the bottom. So on the right is the polarization degree, and on the left here is the magnetic field, which is perpendicular to the polarization angle, mapped onto the flux. So from these maps, they're able to see a toroidal magnetic field structure, as well as polarization degree flux asymmetries, where we see high polarization degree in the northeast and in the southwest. We have also been able to measure the polarization at 2 phase bins in the main pulse and 1 in the interpulse for the pulsar, with polarization fractions of 10 to 15%. There's also a hint of a polarization sweep in the main pulse, but more phase bins would be needed to confirm this, as well as greater than 1 sigma deviations from the optical polarization, which is shown in the black points here. And that's quite interesting because it's a sign that perhaps there's different emission sites or emission processes that are generating the polarized light at these 2 energies. Oh yes, I forgot to mention that if you have any questions, you can stop me at any time. So the second pulsar wind nebula observed by IXPE is Vela. So Vela has a very ballpark similar spin period magnetic field, and also pretty close to us as the Crab pulsar, but it's about 10 times older. It also has a rich X-ray pulsar wind nebula morphology. So here on the image on the right here is the Chandra image of Vela. The pulsar is located at position 1, and then you can see inner jet, and an inner counterjet at 4 and 5, as well as an outer jet and counterjet at 7 and 8. This outer jet at 7 reaches 2 arc minutes from the pulsar, just to give a sense of scale. And then we also see these 2 ridges of arcing emission, 2 and 3. So that's the double torus, as well as 6 and 9, which are diffuse X-ray emission around the pulsar. So in the radio, high levels of polarization have been detected from both the nebula and the pulsar. So at 5 gigahertz, they've been able to measure a mean polarization fraction of 60% across the nebula, with the RMS value about 10%. And at 1.42 gigahertz, at the pulse, the polarization fraction is about 95%, where they also see an approximately linear 90-degree polarization angle sweep. And this has been interpreted as the projection of the magnetic pole sweeping across our line of sight, which has also been known as the rotating vector model. By contrast, in the optical, only low values of polarization have been measured. So with HST, the optical spatially resolved polarization measurements reveal like a very low nebular surface brightness, both polarized and unpolarized. And for the pulsar, they were able to measure a multi-day average polarization of around 8%, with an angle that's about collinear with the proper motion and spin axis of the pulsar. So in this context, we've gotten 800, IXPE has observed Vela for 860 kiloseconds in April 2022. And a polarization map with 5 by 5 30 arc second pixels, shown here, was obtained. And high polarization reaching up to like 60% in these 2 pixels here were measured. So this value is close to the theoretical limit of synchrotron polarization. The measured photon index in this arc jet region, so the inner parts of the nebula, is about 1.3, and it reaches up to 1.7 in the outskirts. And that predicts for a maximum polarization, assuming synchrotron, of 66 to 72%. For comparison, in the radio polarization is also overlaid here, shown in light gray. And that, similar to the polarization angle from IXPE in black, has a curving structure that's symmetric about the pulsar spin axis. But its radius of curvature is behind the pulsar, where there's no radio emission. So that suggests to us that the radio emission probes an older, cooler electron population. Also, So, and then also if the spatial integrated polarization as a function of energy seems to show a slight increase with energy. And that might be explained by the higher energies selecting for a smaller inner region of electrons, where in the nebula, where the magnetic field orientation has less variation. Integrated across the nebula, we find a polarization fraction of 45% with a polarization angle of 130 degrees. And overall, the high polarization fractions and the symmetry in the polarization angle, those things suggest that the magnetic field is highly structured and ordered, and that there's little turbulence in the nebula. IXPE was not able to measure the pulsar polarization. It has a low flux. That's about 10% of the total number of counts in this region. And it's also believed to be mostly thermal emission. Yeah, so, and also assuming that, considering that the optical polarization for the pulsar was fairly low, and if we assume that there's an analogy between the optical and the X-ray polarization, then we would expect that the X-ray polarization for the pulsar would also be small. Yeah, so the next PWN that was observed by IXPE is MSH 1552. So this pulsar wind nebula is powered by a 150 millisecond pulsar, with a slightly higher than average magnetic field of 10 to 13 Gauss. It's located more than 2 times farther away than the crab, but it has a larger spatial extent, so about 15 arc minutes by 7.5 arc minutes, which makes it almost 10 times larger than the crab. The pulsar wind nebula has filamentary structures in the north that extend upward to a thermal H2 region up here. And then closer to the pulsar, we can see an inner arc as well as an outer arc that might be the distorted equatorial torus, or it might be backflow in the PWN that's coming back and hitting against the termination shock. And then to the south, there's also an X-ray jet that extends about 5 arc minutes, and it's bracketed by a sheath emission that's right in the radio. And altogether, these emission features in the nebula form a likely resemblance of a hand. And that's why it's been nicknamed the cosmic hand, or hand of God. So here I've mapped on the magnetic field vectors as measured by IXPE. So IXPE observed MSH for about 1.5 milliseconds. And in the X-ray polarization map, we find that the magnetic field is aligned with the fingers, as well as the curvature in the thumb and the outer arc. And in these regions, we see polarization fractions of 20% in the fingers and 30 and 35% in the thumb and outer arc. For the jets, so the jet region has the hardest spectrum of all these regions. And there we see that the polarization fraction increases as we move away from the pulsar. The magnetic field also acquires an orthogonal component to the jet axis, and it reaches a maximum deviation from the jet axis in the middle of the jet of around 50 degrees. For the pulsar, we were only able to detect polarization at the peak phase, but it can still be useful for constraining the spin axis and the field geometry. So this is a Chandra image of the innermost part of the nebula. So we see a pulsar in the middle, we see the inner arc wrapped around the pulsar. And then in the upper left corner, we see more faintly the outer arc. And from the ellipticity of the torus, we can constrain the spin axis, which is believed to be, or measured to be, along this red arrow here. But whether the inclination angle is 60 degrees, meaning that the southeast jet is pointed towards us, or 120 degrees, meaning that the northwestern jet is pointed towards us, both are viable possibilities. We can do a fit to a rotating vector model fit to the radial polarization to determine what is the best fit parameter for the spin axis. And we can use the IXPE measurements as an additional constraint. So if we place priors on the spin axis, so either 60 or 120 degrees inclination, and we also put in a prior where the magnetic field is perpendicular along the spin axis, then we found that the model favors a inclination of 60 degrees with an orthogonal field. However, the other possibilities are still within the realm of possibility. So the chi-square value for this most favored model is 1.13, but we also found a chi-square value of 1.19 for a model for a scenario where the inclination is 120 with a orthogonal field, and a slightly higher chi-square value for an inclination of 60 degrees with the field parallel to the spin axis. More IXPE measurements, as well as more radial polarization measurements would be helpful to better constrain these parameters. Okay, thanks. So last pulsar wind nebula is BO540. So it's the nickname Crab's twin because it has similar characteristics to the pulsar, as well as a similar torus and jet morphology in the nebula, as you can see in this image here. We've only had a few polarization measurements. So the optical phase average pulsar polarization, as well as the spatially integrated nebula. We've also been able to map out the polarization in the nebula using HST. So here we have the black, the semi-major axis, and then the red are the polarization angles, polarization vectors. So IXPE observed BO540 for 850 kiloseconds. And there we are only able to get a upper limit to a polarization when we integrate across all phase and energies between 2 to 8 keV. But if we restrict to just looking at the off phase regions and in the 46 keV energy range, then we find a polarization angle that's consistent with the optical and a slightly greater polarization fraction than the Crab Nebula, which may be just due to our nearly edge-on view of the system. For the on phase, if we look at the on phase in 46, then we find a fairly high polarization fraction. And using a more sensitive method, we found that the polarization degree at the edges of the pulse are between 60 and 70%. And we also found lower significance around like 2.9, 2.6 sigma measurements of the polarization fraction of 45% in the middle of the pulse. And that has an interesting correspondence to the dip in the single broad pulse here. That might be interpreted as the overlap of two cones of emission with different polarization angles, leading to a lower polarization fraction in the center of the pulse. Yeah, so that kind of summarizes the IXPE results for pulsar wind nebula. And I've kind of summarized those results here. I just want to briefly mention that there are 2 upcoming IXPE studies that are coming out. So one of them is the crab observations, including the 2023 data. That's hopefully coming out later this year, as well as analysis of the supernova remnant G21.5. So yeah, I'll stop there, and I'm not sure how much time we have for questions, but yeah, thanks.
Thanks, Josephine. We do have a few minutes for questions. Should I turn this off? Any questions from the audience? Yeah.
Hi, very nice talk. At some point you mentioned a polarization fraction of 95% for pulsar emission, right? So that is not synchrotron emission, or what kind of emission mechanism allows such high polarization fraction?
Yeah, so that would be some kind of coherent emission. I think that we're still not quite certain, like, what is the cause of such high polarization fractions in the radio, but it would be some other different kind of emission that's responsible. Yeah.
All right, thanks.
Josephine, I had one, and I don't want to make you go all the way back through your slides, but I think for the crab pulsar, you had indicated that the profile deviated about 1 sigma from the optical profile.
Yeah.
And which isn't much, and so I'm curious as to whether there are expectations for potential deviations based on models that might be used to ask the question, do the deviations match what the expectations are?
Yeah, so right now, I've been kind of working with a striped wind model to try to explain differences. So here's the yeah, so in this plot here it says it's just greater than 1 sigma, but there might be, due to the size of the phase bins, which are much larger in the X-ray, there might be some depolarizing effects going on. So the deviation might be a little larger. But yeah, we're playing around with different scenarios with the striped wind model to see if that might be able to explain the differences in the polarization at the 2 energies. And it's a possibility that perhaps the optical is probing like regions that are farther out from the light cylinder, and X-ray is probing regions that are closer around the light cylinder. But yeah, we're still kind of investigating that.
Okay, thanks. Any other questions? Okay, thanks Josephine again.